Okay. Good evening, everyone. I hope all of you enjoyed a beautiful sunny day here at Buffalo today. So with that, I'll start my talk. So as a disclaimer, my background is not in wireless communication. I'm more of a user of wireless communication. Um, Rather, we develop several methods for coordinating multiple robots, multiple aircraft, and so on, where we make certain assumptions that certain capabilities are available from wireless communication, and then we run with our algorithms. So the whole point of my presentation today would be, I'll be talking about some of our work in multi-robotics, multi-UAV operations, as well as the new concept of urban air mobility. And with every project, I have a last slide, which kind of talks about the communication assumptions that we made. The whole point being kind of opening up the platform to communication experts, like most of you, to kind of identify if this is doable with the current technologies, or what the new technologies need to be to support this kind of multi-robot, multi-aircraft operations that are being envisioned by folks like us. So that's kind of my goal today. And feel free to critique the requirements. I'll be happy to get that feedback on the communication aspects. So I'll kind of cover these 4 areas of work, starting with realistic robot swarm operations. Then I'll talk about more specific multi-operations, example, task allocation in a disaster scenario, or searching for signal sources to find a victim, or localizing hazards, and so on. Then I'll move to kind of a aerospace application, talking about urban air mobility, which is this new concept of using electrified vertical takeoff and lift aircraft that can carry anywhere from 2 to 5 passengers, basically flying taxis, if you want to think about it. How do we create networks of this? Obviously, communication has to play a very important role in making that happen. And I'll talk about 2 different problems in that urban air mobility area. And this kind of an area that's kind of really emerging, and the work that I'll be presenting is very recent, even from our end. We just have probably just the first a couple of conference papers coming out of this in the last year or so. So start with kind of realistic robot swarm operations. These has to do with operations catering to various domains, from disaster response to military operations. Mostly we use teams of robots doing these operations because they are often time and cost efficient compared to using multi-million-dollar single standalone assets. They are more resilient than those single standalone assets. And they typically tend to be more task and environment adaptable than existing sophisticated assets. So you're talking about a team of very simple unmanned aerial vehicles or ground vehicles or subsurface vehicles and so on. However, it's easier said than done. There are several challenges. It's very challenging to scale techniques that can coordinate tens to hundreds of unmanned aircraft or ground vehicles. Also, it becomes difficult when your team is heterogeneous, for example, includes different types of aircraft or aircraft and ground vehicles together and so on. Also, most of the work in this domain, even over the last 20 years, tends to focus on a single behavior, like foraging or just search or just task allocation. The issue with that is most realistic operations cannot use a single behavior. They need combination of behavior. So we are probably among the very few starting to do combination of various types of multi-robot behavior or swarm behavior, so you can construct realistic operations, which has been till date very difficult to accomplish. And finally, most of these operations occur with some human intervention, often at the supervisor role as opposed to operator role, because most of the individual aircraft or ground vehicles are fairly autonomous. They only need kind of high-level supervision, but there still are significant challenges in that supervisory role of humans and how you make that interaction happen in an effective, timely manner. So moving on to the first project I'm talking about, this was a DARPA offset program, but the goal was to command and control teams of 50 to 100 unmanned aerial and ground vehicles, UAVs and UGVs, performing search and rescue operations in an urban environment. This adversarial environment, that means there are adversaries who are trying to neutralize your agents, so you have to adapt to that. This was a fairly large program. Our responsibility as a participant was mainly to develop AI techniques for strategic decisions guiding the behavior of this team of UAVs, UGVs. An example scenario is given here, where you have 9 squads of UAVs and UGVs. Each of them needs to be tasked to go and search different buildings to find out that building which contains a victim that you need to rescue and extract. There are many potential buildings, and that needs to be searched. It's a fairly complex environment that you are talking about. And there are certain specifications that you have to cater to in terms of the capabilities of the individual agents operating in that environment. This is the overall framework, kind of a crowded slide, but just to give you a very high-level understanding, this is the overall learning framework. It's a reinforcement learning approach. We apply a couple different methods. We apply both evolutionary reinforcement learning, the neuroevolution, as well as policy gradient techniques. There are pros and cons, which I won't get into, but the whole idea is you look at the state of the mission in terms of the state of your agents, the observable state of adversary agents, and the state of the environment. There are obviously dynamic factors in the environment like smoke, certain gates can be open or closed, and so on and so forth. Based on that, the tactical AI model, which is a policy model, takes a decision as to the actions. What are the actions here? The actions are how to group my team of 50 UAVs into, say, 6 squads, and what tasks to allocate them. Like, you go and search this building, or you go and do perimeter defense of this building, and so on and so forth. So you can see it's a fairly complex problem at that scale that's being solved. So moving on, kind of showing you one of the example results, just to give some perspective. The video shows the motion of the UAVs, UGVs, which are the green dots and the blue dots. The red dots are essentially adversary units, which can also be thought of like adversary UAVs, which are trying to neutralize our own agents in that case. And you want to either avoid them or engage them, depending on the needs of the mission, which is itself a part of the strategic decision making being done by the RL trained policy in this case. So extremely dynamic, uncertain environment is where we are operating in this case. Looking at some of the results on the right-hand side, where the goal was to kind of minimize the overall rescue time, and the complexity of the policy network increases as you are trying to do that in this case, and you can see kind of the entire cycle as it happens. The overall learning and training and testing occurs over a simulation environment. So you kind of look at the state of the mission on the simulation environment. Based on that, you take a decision which gets executed in the simulation environment, and this process repeats. Sorry. We also learn from humans, so we have an entire gaming interface as well, which goes over the simulation environment. So simulation environment is simulating the motion of robots and the formation and task allocation and so on and so forth. And then there is a gaming interface through which a human can give tactical inputs. The goal of that is to see how the human tactical inputs differ from AI-based inputs. And in the long run, if humans have an advantage in, for example, contextual reasoning, then we want to be able to imitate part of that. I'm not going to get into that. That itself is like a 1-hour talk and how we use human inputs to improve our AI policy. But we also have that capability in this context. At the same time, you can simply use the humans as tacticians, which is probably the lower hanging fruit in deploying these capabilities into the field for both emergency response or military applications. Now, coming to the communication constraints in this case. So there are certain assumptions that we make, and depending on the type of information being shared, the requirements are slightly different. I have mostly put it in kind of qualitative perspective. The fastest communication requirements are with the formation control. When you're flying each squad in a formation, you need almost no latency and no downtime in information exchange between the agents in each formation. Okay. Then in terms of the information exchange between the centralized tactician, whether it's a human or AI, and the overall team, you have a little bit more leverage. There can be some latency. The information exchange is also fairly low in terms of GPS coordinates and so forth in this case. Finally, we made some estimates based on the requirements in terms of the size, and it seemed that the requirements could be made by a 5G or future 6G kind of a wireless environment, as long as that capability is available. Although in many disaster response or military operations, such capability may not be available, and we might be depending on an ad hoc network to support that entire operation. So something to think about. Moving on to the multi-robot applications, the first application that I'm talking about is a task allocation application, where the context is there's a flood and you're responding to victims in that flood. So you're basically delivering medical supplies or life vests and so on at multiple locations. So there are hundreds to thousands of locations that need to be visited by a team of say 20 to 30 drones. It's a very complex problem. Most traditional operations research methods like auction-based planning, optimization-based planning are not able to solve this in any sort of timely fashion. You typically require an AI-driven technique, so you can use real-time policies to solve this, which is fairly established in recent times. And there are a couple of methods that works in this context. I'll talk about our method, but that's kind of the problem context. There are certain constraints in terms of time deadlines. If you don't reach a victim by a certain point of time, then the task cannot be completed. Obviously, the individual robots or drones in this case have their own constraints in terms of range, communication, and so on and so forth, which you have to be aware of and make sure they're implemented within the environment. So we solved this problem using a very new kind of architecture that we developed through an ongoing ONR project called a capsule attention network. So the best performing existing method uses an attention network, which is based on kind of the work in natural language processing for solving combinatorial optimization problems. We somewhat improve on that by adding the capsule-based encoder. The purpose of adding that encoder is it's better at encoding local structural information. So we kind of think of the entire task space as a graph, and we encode that using the capsule network in a manner that is robust and scalable, which was previously difficult to accomplish. And what this accomplishes is that you can learn on a smaller network of say 100 nodes, and you can apply that policy on a network that is 200 nodes without retraining, which was a significant improvement, because that saves you on the training time and the number of scenarios you require to train for this kind of complex real world problems. There's some of the results. I won't go into it, but basically we show that the policies are real-time executable. They are at par with other non-learning based solutions, which are based on methods such as different heuristic search, optimization, auction-based methods, and so on. So you can match their solutions while being much faster than them. Some of the communication requirements in that context. So we expect the range for this kind of a disaster response application to be about 1 to 10 kilometers, the latency to be less than 4 seconds. There can be some downtime, like 30 to 60 seconds. The data sent per message is not high. It's about 6.4 KB per robot for a 50 robot team working on a 500 task application. However, for our application, it was slightly scaled down, and we assumed a range of 500 meters in the ideal scenario. And when we decreased that range to 100 meters, we saw a significant drop in performance. So in real world problem, you can think of it as instead of a 10-kilometer range, if you had 2-kilometer range, you would see a 25% drop in performance. But drop in performance means instead of meeting 100 tasks, you are only able to meet 75 tasks. So you are only able to deliver supplies to 75% of the victims in that flood scenario, which is a significant drop in performance because of deterioration of the communication. So this is something to think about from the wireless perspective. I'll skip over this application. This was basically a search application where you're trying to find skiers trapped under avalanche. I'll just go to the communication requirements for this application. So you're basically deploying a team of 5 UAVs, running one of our algorithms to find skiers trapped under an avalanche. And each of those skiers has a IR beacon, which you can track. In this case, for the team to coordinate, their communication range should be about 500 meters at a minimum, about less than 1 second latency. That's very important, less than 5-second downtime. The data sent could be low if you are just detecting IR signals and mostly reporting that and the GPS coordinates, so it's 160 kilobytes. However, if the search in such an application is going on based on visual search, you could need up to 100 megabytes data to be transferred in every message across the drones and between the drones and the central nodes. So with that, I'll move to the urban air mobility applications. The two urban air mobility applications that I'll talk about, this is out of very recent research that we have been doing over the past a couple of years. So for those of you who are not acquainted with the urban air mobility domain, so essentially it's the concept of using air taxis. These are electrified vertical takeoff and lift aircraft. There are probably about a dozen startups or mature startups across the world. Half a dozen of them are in US who are launching vehicles that can do this at different stages of development. There's pilots going on right now in Dallas and the West Coast as well. For urban air mobility, the expectation is you would be operating hundreds of these in the greater metropolitan areas and even across intercity areas, for example, between LA and San Diego, or the entire Eastern Corridor, where you have a density of several big cities, so that transport can occur much faster than by road. And there's also a net emission reduction in that case. So that's kind of the vision of urban air mobility going ahead. Obviously, there are several challenges. For this to work, fleet management is extremely important. Safety is probably the #1 barrier. How do you safely manage this traffic of aerial vehicles in dense urban airspaces? This has never been done in general aviation. So that's a new challenge. Obviously, this urban air mobility vision can only be realized if we are talking about level 4 or level 5 autonomy. And that will only work when you have a very reliable communication network supporting it. So that's why it makes it a really good case study or a problem. Vision wireless. So the first problem we are looking at is basically vertiport traffic management. So a single vertiport located on a parking area or a really large high-rise building, the single vertiport is expected to have probably about half a dozen pads, like helipads. Some of them are for landing takeoff, some of them are for charging, because each of the aircraft, when they land, they have to also charge so that they can go for the next flights. And you can expect that within the cone, and think of it as a virtual cone of operation of each vertiport, you will have dozens of aircraft up within that cone, some of them taking off, some of them landing, some of them temporarily hovering or loitering because you cannot give them a landing spot yet, right? So that's a very interesting problem. Again, a real-time problem where optimization-driven methods often fail because they cannot work that fast. So you kind of you depend on policy-driven methods, which is also challenging because you're talking of assured policies, which is a different discussion altogether from here. So we kind of develop, again, a graph RL-based policy in this case to decide the allocation of who will take off, who will land, and so on. The criteria is minimize the delay based on the previous schedule, preserve safety, be aware of the battery constraints, how much remaining battery on each aircraft, and so on. So those are the additional constraints in this case. Going ahead, we plan to also include uncertainties due to weather and so on. So this is kind of the overall network. So we kind of see the vertiport with multiple pads as a graph, and we also look at the different aircraft within the cone of that vertiport also as a graph. This goes through a graph convolutional network, and then that information goes to a separate policy network and a value network in order to decide the optimal actions, which is land, take off, temporarily hover at this particular location, or loiter at this particular location, and so on, which are the decisions resulting from the policy. This is a visualization of the simulation environment that we use. We use typically the AirSim environment, which is based, which is a Microsoft product based on the Unreal gaming engine. So you can simulate at least kinematics. You can also do dynamics, but obviously simulating things at the level of dynamics would make the simulations too expensive to do any sort of RL, even with the best computers at our disposal. So we do up to kinematics in these cases. Some of the results, without going too much into it, basically we lower the number of collisions is better, lower the delay is better, takeoffs, landings, battery higher the better, and we kind of compare our policy, which is GRL, with a more traditional RL agent, a random agent, and a more traditional solutions in this case.
Okay, great. So do you mind if we touch the high levels a little bit, because we are a bit behind the schedule now?
Yeah, so I'll wrap up
if you can just
pretty much
touch
with
the
this one.
high level, it would be awesome. Thanks.
Yeah, so I'll wrap up with this and just one more slide. So for this, the communication requirements is almost close to zero downtime, less than 2 milliseconds latency, because you must want to be almost on continuous contact with each aircraft within that cone of that vertiport. Very low packet loss, and the communication range should be about 0.5 to 1 kilometer, centered around that vertiport and talking to tens of vehicles in that location. So skip the last application, which is kind of the fleet management. I'll just go to what are the requirements for fleet management. So fleet management is occurring across basically multiple vertiports. Think of the entire New York City area. So in that case, the requirements would be obviously spread out, wireless communication over 20 to 70 kilometers, where you obviously are talking to 50 to 100 aircraft. Ideally, they should be able to talk to each other as well, maybe through some central nodes. Slightly more latency is allowable, about less than 5 seconds. Some downtime is acceptable in that case. And the data that you want to be sent is fairly compact, about 20 kilobytes per message, mainly GPS coordinates and some other state information of the aircraft. Unless obviously some emergency occurs. If some emergency occurs in this scenario, you want to allocate situation adaptively more bandwidth or more messaging capability to that particular aircraft, probably in the order of hundreds of megabytes per second. So with that, I'll finish up with one of the facilities that we have at UBuffalo for doing these kind of experiments, where we plan to test some of the methods that I showcased. So if any of you are interested in testing multi-UAV, multi-ground vehicle networking, you can use this space. This is a fairly large space that we have here. And we are actually moving ahead with instrumenting this facility with outdoor motion capture. And there's also plans to include wireless communication, and I'm open to suggestions as to what wireless communication would be useful in installing in this facility. And we have a AFOSR DURIP grant that we can use for that purpose.
Great.
So with that, I'll end my talk, and I'll be happy to take any questions or comments.
Thanks, I appreciate it. So there is just one question because we're a bit behind the schedule. It popped out on slide 9. And the question was, is the learning framework based on an observable, pattern-based framework?
I'm not 100% sure what you mean by an observable pattern-based framework. If we are talking about the observability of the mission state, we have only partial observability of the mission state. You do not have like an eye in the sky. That's not realistic in many of these applications. So you only know like the GPS locations and the state of each of your agents, and you only have very limited information about the locations and state of the adversarial agents, and you use that partial information to kind of plan your tactics. So I would say this falls into the category of doing your tactical planning in a partially observable Markov decision process, so like a POM-DP kind of environment. Yeah.
Okay.